For Chapter 14, Exercise 5C, it says, show what reagents you would use to prepare each of the following ethers via a Williamson ether synthesis, and explain your reasoning and draw the mechanism for the reaction. So how can we make this molecule here? You'll notice the ether oxygen here. The Me on one side, that's standing for methyl, so that's a methyl group. In other words, that would be like having the rest of the molecule, and here a CH3. That's the methyl group. And so to make an ether, which is what this is, you can see this is the ether oxygen with a carbon on both sides of it. To make an ether, you can make it from an alcohol and an alkyl halide. So draw sort of a line down the oxygen, and we can put the alcohol and the alkyl halide on either side. So for example, let's say we take the left side of this and we put the alcohol there. So that's one possibility. And if we put that on the left side, then the alkyl halide would have to be on the right side. And here I'm using chlorine, but I could also use bromine or iodine. Any halogen, that would be a good leaving group. So that's one possibility. Another possibility is the alkyl halide is on the left side instead of the alcohol. So we'd have that, and then the chlorine there, and then we'd have the alcohol on the right side. So like this. So these are two possibilities, and if you go back and review the part A and B for this exercise, you'll remember that this Williamson ether synthesis happens through an SN2 mechanism. And with an SN2 mechanism, crowding is really important. The nucleophile has to attack the carbon that has the halogen, or the leaving group on it, and in order for it to attack that, it has to have space around it. And so you want to look at the carbon that has the halogen attached and ask yourself, how many other carbons is that attached to? Now on the left here, that carbon is not bonded to any other carbons. There's so much room around here for the nucleophile to attack. This is actually a methyl group, which is has the least crowding of any type of carbon. On the right, if you look at the carbon that has the leaving group, or the halogen attached to it, that's bonded to 1, 2, 3 other carbons. That's tertiary, so that's really crowded. There's a lot of, to use the fancy terminology, steric hindrance. Steric hindrance just means crowding. There's a lot of steric hindrance around that. So that would really not work very well for an SN2 reaction. So we're not going to use this possibility on the right. We're going to use the ones on the left. So we've identified the reagents we're going to use, and the reasoning is we're going to use those because the alkyl halide here in this version is less substituted, and so the SN2 reaction will be more efficient. Okay, so this is what we're going to work with. Now, we have a nucleophile in the alcohol. After all, it has the lone pairs, and it also has a slightly negative charge because the oxygen is really electronegative, so it pulls the electrons in that bond towards it. And it makes the things it's bonded to, the hydrogen and the other carbon, slightly positive. It steals the electron density from them a little bit. So that is a nucleophile because it has the negative charge and the slightly negative charge and the lone pairs. But it's not an amazing nucleophile because the charge is not a full charge, it's only a partial charge. So to make it a better nucleophile, in order to make the reaction more efficient, we're going to add a base, and the base is usually sodium hydride. This is an ionic compound where the sodium is a cation and hydrogen is an anion. You may look at hydrogen and think hydrogen is not a particularly electronegative element. Why would it be stealing the electrons? And the trick is, if you ever want an element to get electrons to get a negative charge and to act like a nucleophile or a base, you just have to pair it with a metal. Because the metals have such low electronegativity, they'll just give their electrons away to anything, even if it's something you don't usually associate with being very electronegative, like hydrogen. So this hydrogen is very small, smallest atom on the periodic table, and it has a full negative charge. It has to fit in that tiny space, so it's very reactive. It's going to react with the first thing it comes across, and the most available thing is this hydrogen here. It has a slightly positive charge, and there's very little crowding there, and the bond that it has is easier to break than any other bond here, because it's already partly broken. The electron density isn't evenly shared. So the hydride, hydrogen with a full negative charge in a lone pair, attacks the alcohol hydrogen. This hydrogen can only form one bond. It already has a bond, so it's going to make a new one. The bond that it has to break. Those electrons go to the most electronegative place nearby. That's the oxygen. And so we would get this alkoxide. Oops, let me actually do this. These were the original lone pairs that were there. And then the bond turns into a third lone pair. Altogether they have a negative charge. That's an alkoxide. An alcohol that's missing the hydrogen has a negative charge instead. And you'd also have hydrogen gas, H2, and that would bubble away and go on to live a different life. So now that you have the alkoxide, you can introduce the alkyl halide. The alkoxide is an awesome nucleophile because it has a full negative charge. And so if you look at where it might attack on the excuse me, on the alkyl halide, chlorine is just underneath fluorine on the periodic table, so it's pretty electronegative. It pulls the electrons in the bond towards it, becomes slightly negative, and the methyl group, the carbon there that it's bonded to, is losing that electron density, so it becomes slightly positive. And so this negative charge on the alkoxide attacks that slightly positive carbon. Carbon can only form 4 bonds. It already has 4, so if it's going to make this new one, it has to break one of the bonds it has. And the weakest bond that it has is this one right here to the chlorine. And so the chlorine, that bond breaks, the electrons go onto the chlorine. This chlorine already had 3 lone pairs. Now it's going to have a 4th. So you'll have that alkoxide turning into, on the other side of it, you'll have the CH3, and then you would have the chlorine with its full negative charge, which would probably pair up with the sodium. Now remember, we're drawing individual molecules here, but this would be happening to a population of these molecules. There would be hundreds of millions of all of these, and so some of the chlorines will jostle through the solvent and meet up with the sodium and may stick with that. But the key and important thing, the thing of interest, is the ether that we formed. So you've got the oxygen with carbons on both sides, and that was the ether that we wanted to form in this Williamson ether synthesis.